Today I will show you the undisclosed capabilities of a VIC-20. I will compare these with the capabilities of an Arduino and find out whether this computer is still of any practical use nowadays. So stick around. Back in the 80s, the VIC-20 was a very popular computer among makers. This was because the VIC was rather inexpensive, as it had no fancy sound or graphic capabilities like the C64.
A computer that plays great games?
Under $300? Exactly. We didn't know.
And thanks to its MOS 6502 processor running at 1 MHz, it had a quite decent computing power for the time. Looking at its backside, we see a board connector where various peripherals like a joystick or a light pen can be connected. Also, there are 8 digital I/O pins that can either be programmed as digital input or output. And here we see a typical home computer setup of the 80s. Monitors were expensive and rare, so people often used portable TV sets as monitors. These had generally no video input, and that's why there was an RF modulator necessary. Because of this, the picture was blurry and the colors looked washed out. For my VIC-20 the modulator got lost. So I did a bit of tinkering to an ancient black and white TV and feed the composite signal directly in. This way we get a sharp and crisp picture. On the VIC-20 you can simply type in your programs, then enter run, and there we go. But over time this way of working becomes tedious. Staring into this flickering TV will burn your eyes, and the programs are hard to read and quickly become confusing because of the poor screen resolution of only 22 by 23 characters. So I was searching for a way to develop the programs on my PC and then transfer them to the VIC and run them there. In the solution that I came up with, we can code and build the programs with CBM Proc Studio. This IDE allows both basic and assembly programming for all Commodore computers. After writing the code, we can test it in the VIC emulator. But how can we bring the programs over to the real thing? Remember that there is no USB connector. There is no SD card slot either. But we have the cassette port. Why don't we use this to transfer the programs? We just need to generate the signal that comes out of the data set with a PC and feed it into this port. To do so, we need to convert the PRG files that come out of the IDE into Nerd's music, and I found a handy tool that perfectly does this. Choose your machine in the drop-down menu, check sound card, browse to the program file and double-click. But just feeding this into the cassette port will still not work. Looking at the signal with an oscilloscope, we find that it is not what the VIC-20 wants. What we want is a more or less clean rectangle wave with at least 3 volt amplitude. To get this, I made a simple comparator circuit which plugs into the tape port of the VIC-20. You can pause the video here to copy the schematic if you want to build this for yourself. Okay. To wrap it up, plug in your adapter, also the headphone jack, then type your program, generate your project, type load on the VIC-20, select the machine and sound card, now also the project file, wait a bit. Now the VIC-20 is searching for a program. He found it now and loads. And here we are. And here we have the Arduino setup that competes against the VIC-20. Just plug in a USB cable, start coding with the IDE of your choice, upload the sketch, and that's all. Much faster and simpler. The VIC-20 has 2 MOS 6522 I/O chips, also called Versatile Interface Adapter or VIA for short. The first one interfaces the keyboard, the serial floppy port. The second one is for the tape port, joystick, and also the user port. Here we have 8 out of the available 16 digital I/Os at our free disposition. These can easily be accessed by an edge connector. I want to let an LED blink now, but because the wire can only deliver a few milliamps, we need a transistor to even drive a small LED. An Arduino pin on the other hand can provide up to 40 milliamps. Now I go ahead and write a blink program in BASIC. The port can be controlled by 2 registers into which we can write 8-bit values using the poke command. I already connected pin 7 to the gate of my transistor, so we need to set this pin as an output. This can be done by setting bit 7 in the data direction register, which means poking the value 1 to 8 into address 37138. Then I turn the pin on by setting bit 7 of the output register at address 37136. BASIC has no delay function, so I let the CPU spend some time in a for next loop. After that I reset the bit to turn the LED off. Wait again for half a second or so. And finally let the VIC-20 do this over and over. The run command starts the program and it does what I expect. Now let's run a speed test. I remove the for loops to see how fast it can blink. Entering a line number deletes a line. Okay, seems to be too fast to be seen by the human eye, so let's clamp on an oscilloscope and measure the frequency. 64 Hz! Wow! Now the Arduino. Here I alternately set and reset the output in the loop function, download and attach the oscilloscope and get 2 MHz. Wow! But this battle is not fair. BASIC is an interpreter language. That means that the computer spends a lot of time determining what to do with each instruction before it actually executes it. The C program of the Arduino, however, is compiled to machine language and so it executes without any additional load. So let's write a small assembly program for the VIC-20 and see how fast it gets now. Almost 74 kHz. That's more than 1000 times faster than the BASIC program, but still 27 times slower than the Arduino. The 6522 has also 2 16-bit timers. One use case of hardware timers is the generation of pulses modulated signals. These can be used for controlling DC motors, for example, but also other fancy things can be done with PWM, like making music or AM broadcasting, what I already showed in earlier videos. Getting PWM out of a VIC-20 is kind of tricky. Here we need to configure a 6522 to fire an interrupt when its counter value reaches 0. Then we need an interrupt service routine that alternately restarts the timer with 2 different start values. I coded a small program where I can enter a frequency and a duty cycle and so set the speed of a small gear motor. If you don't know what duty cycle means, it is the percentage of time when the signal is high. The higher I set the duty cycle, the faster the little guy rotates. 100% is always on, 0% is off. Maybe you wonder about this nervous animation here. This is drawn by the BASIC program into which I enter the values and which passes these over to the interrupt routine that creates the PWM signal. Right, both the animation and the PWM generation routine run in parallel like 2 threads. We actually implemented multi-threading on a VIC-20.
No. Yes. Oh.
Let's find the maximum frequency that we can get out there. I start with 3 kHz and the animation runs fluently. Now 4 kHz. Seems to be a bit slower now. 4.5. It gets noticeably sluggish. And that's because the processor spends most time in the interrupt routine and has less and less time to draw the animation. 5 kHz. And the CPU spends all the time in the interrupt routine, and whatever key I press, the computer doesn't react anymore. The output frequency is stuck around 4.7 kHz, not really high. And that's why we cannot use the VIC-20 as synthesizer or AM transmitter. Now look at the 3 timers of the Arduino. These can be configured with an additional threshold, so they can output a PWM signal on their own without the need of any time-consuming interrupt routine. With this they can go up to 8 MHz. The VIC-20 can read analog values through its control port. There we have 2 pins which are dedicated for game paddles. Basically, a game paddle is a potentiometer that forms an RC element together with a capacitor that's built into the VIC-20. The capacitor is slowly charged through the paddle's actual resistance. When I slowly turn the resistance down, the capacitor charges up faster and so reaches a threshold of around 3 volt earlier. At this moment, an 8-bit counter value is copied into a register and can now be read by an application. This value represents the time that's needed to charge the capacitor and is proportional to the actual resistance. When the counter reaches its maximum, the capacitor is discharged, the counter reset to 0, and the whole process starts over again. This happens about 2000 times per second, so the sample rate is 2K samples per second. We can replace the potentiometer by a photodiode and program the VIC-20 as twilight switch. How silly is that? In contrast to the VIC-20's control port, the Arduino's AD converter can be multiplexed so that up to 8 parallel analog inputs are available. Its resolution is 10 bits and it can sample up to 79K per second. And once more the winner is the Arduino. Okay, the Arduino is so much better in all respects. But maybe you still have a VIC-20 laying around and your control task is not too demanding? Then consider that the VIC-20 has no flash memory to permanently store the programs on. This means that every time you power on your computer, you need to load the program into memory, and that takes a while. And if your application runs over a long time, you also need to consider the power consumption.
How dare you!
At least it is a good heater. Over 50 degrees Celsius. Also the chips get remarkably hot. Okay, that's all for now. Thank you for watching and see you in the next one.
Under $300, the wonder computer of the 1980s, the Commodore VIC-20.